Okay, hey guys, welcome to our first LeetCode video. Today we're going to do 2130 maximum twin sum of a linked list. So in this problem, we're given a linked list of size n where we're told that n is even. The ith node of this is zero index, so the ith node of the linked list is known as the twin of the n minus 1 minus ith node if 0 is less than or equal to I is less than or equal to n over 2 minus 1. So essentially, this is just telling us that if I is in the first half of the list, the twin of this ith node will be the n minus 1 minus ith node. And twin is probably associative. So that means n minus 1 minus ith node is the twin of the ith node if I is within this range. So twin sum is defined as a sum of a node and its twin. We're given the head of a linked list with even length. So we're guaranteed that each node will have a distinct twin. We want to return the maximum twin sum of the linked list. So the way I'm going to approach this, I think the optimal time complexity we can reach is O of n. And the reason is, or what I mean by that is the most efficient algorithm we can hope to come up with will probably be O of n, since this twin sum will look at a node and its twin, and we're going to look at every node because otherwise we don't know what value exists in this node, and a value can directly change or influence what the maximum twin sum is. So we want to look at every value within this linked list. So that being said, I think if we're looking at every value in this linked list, our most efficient algorithm will most likely end up being O of n runtime, or that's the best we can hope for. So the thing that makes this problem challenging is that we're given a linked list, right? If we were given an array, we could access each of these I and n minus 1 minus I in O of 1 time, in constant time. We can just look up what the I is, or what value exists at position I and what value exists at position n minus 1 minus I. So one way we could do this is we could just translate this linked list into an array. We just iterate through the linked list and add each value into an array, or we can even add it to a hash map. I'm going to do it with a hash map right now. So I'm going to say cur equals head, and what this will look like is I'll say while cur. I'm also going to keep track, since this is a dictionary and not an array. I'm going to keep track of what index I'm at. So while cur scene of I equals cur dot val, because this is 0 index and I'm starting at I equals 0, then what I'm going to do is I'm going to advance my cur pointer. And then now that we have that, let's say I equals n, or n equals I plus 1. While, or for other for, we can do for loops another have all the current dot vals, all the vowels in my scene dictionary. I just want to iterate from the front of my linked list to the middle part and just take the sum of each node and its twin node and then compute the max sum. So I'm going to have a variable cur max, and it's going to be the minimum possible value it can be. From here, I'm looking at number of nodes as an even integer, and node.val is positive or greater than 1. So I'm going to say cur.max equals 0, and as soon as I get some number, the very first number will set my cur.max value. So for I in range n over 2, so for the first half of this list, I'm going to say cur max. I'm going to make a comparison. I'm going to check if my current twin node sum or twin sum is greater than my current sum. And if so, I'm going to update it. So this will be equal to scene of I, and I'm going to get scene of n minus 1 minus I. And then ultimately, we want to return cur max. Hopefully this runs fine. Oh no. Oh, sorry, I forgot to advance the I pointer. Oh no. Okay, we don't want to do I plus one, we want to do I because we add one to each thing. So at the end, since I'm always updating one, and then when cur is equal to none, I add one to I again. I don't need to do the I plus one. So that works. But this will be an O of N runtime and O of N space because we are keeping track of a scene, or essentially we're keeping track of an array or a dictionary or hash map where I am adding values that grow linearly with the size of this linked list. So can this be more efficient? Yes, we can. And the thing is, a way to be more efficient than O of N is we maybe don't want to use an auxiliary data structure, right? Because more efficient than O of N would be like log N. I don't see a way that we can optimize this to be log N. So a more efficient solution would be O of 1. And is there a way to do this with an O of 1 space? And the main bottleneck here is we have an I equals 0. We can access the I equals 0 element in O of 1 time because it's ahead of a linked list. But to get the N minus 1 minus that it gets twin, that would be O of N, right? And when I equals 1, well, hopefully once we go from I equals 0, we advance it to I equals 1. So that will be part of our O of N runtime. But to get the next element, since the N minus 1 minus I, the twin of the 0th node was at the very end of our linked list, going back would require us to traverse the linked list again because we can't just go to the left, right? All of these pointers are only one to the right. It's a singly linked list. So we can't just go one to the left. So one way to do this would be to just reverse these pointers, right? Reverse the pointers of the right half of the linked list. That way we can have two pointers, one at the very beginning, one at the very end. And since these pointers to the right half of this linked list are reversed, we can just advance them one at a time until we get to the very end of both linked lists. So let's actually try that real quick. So first, what I want to do is I want to get to the first half of the linked list, right? I want to get a pointer at the very median. That way I have a pointer of reference to the first half of the linked list. I have a reference to that median node, and that way I can reverse from the median onwards, right? So one way to do this would be to set a slow pointer equal to head, a fast pointer equal to head dot next, and this is guaranteed to exist because I have at least two nodes in my linked list. So while fast and fast dot next, slow equals slow dot next, fast equals fast dot next dot next. Okay, so now I have the slow pointer pointing to the element at the very end of the first half of my linked list, right? So now what I want to do is I essentially want to reverse from the first half from the median to the very last element in my linked list. I want to reverse all of these. So what this will look like is if you're gonna define a function to do this, to define reverse, I'll have a start node. And it's gonna reverse from the start on, right? So cur equals start, prev equals none. And while cur while cur for next equals prev equals cur equals next node. Let's do what I wanted to do. So the first element will point to none. Yeah, and then I want to return. I guess I want to return prev. And so why do I want to return prev? Well, prev will give me the it'll give me the head of my reverse linked list. So if it was 5, 4, 2, 1, it would give me the 1. And so that way I could just have 4 point right to 1. Right. So let's say fast equals, because fast is now my advanced pointer. I want a pointer at the very beginning. So now I'll say slow equals head, and then fast equals reverse. Sorry. First, let me do this. Fast equals reverse on slow, and slow equals head. And then now while fast, I'll say current max equals 0, while fast, okay, great. So what I was doing here was I first reversed from the slow because my slow was the pointer right before the second half of my linked list. So I reversed slow and then I got the pointer to this very last node, right? So what I did was I could have stitched it. I could have said slow dot next. I could have had a pointer to start and said, okay, start dot next equals fast. And now I have the entire linked list stitched together, but there was no need for that. Our problem doesn't require us to have a fully connected linked list or anything like that, or we don't need to recover it back. So what I'm gonna do instead is I'm just gonna have that fast pointer just start right there and then reinitialize my slow pointer to start at the head of the linked list, and then have this current max equals 0, which is again this variable that keeps track of the current max sum. And so now I could do while slow dot next, but I think slow is still connected to or like the second half of the linked list is still connected to the head. What I'm gonna do instead is start from the fast because I know this linked list ends at none, right? Because I have prev equals none right here. So while fast curve max equals max of slow dot val plus fast dot val. So these are 2 pointers, current max, and then once I do that comparison, I move the pointers over, and then finally I return current max. So yeah, hopefully that makes sense. I'll see you guys for the next video.